In this lecture, we'll answer on two questions. In the first question, we will find out the area of this green triangle, triangle ABC. And the second question, we will find out the length of this line segment AP that is equals to x. We have to find out the value of x. So we start with the first question. In the drawing, we have quadrilateral ABC PQ. We know that AQ equals to AC. We also know that AB equals to 5 units in its length. This is line segment PC that equals to 4 units in its length. This is angle QPC that equals to 60 degrees in its size. This is angle ABC that is also equals to 60 degrees in its size. This is angle PQC that is a right angle. Again, our task is to find out the area of this green triangle, triangle ABC. So, in the first step, we draw perpendicular from point A to QC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A and QC. This point is point M. Triangle AQC is an associated triangle because side AQ equals to side AC. And here we can implement rule 22. So I'll pick rule 22. According to rule 22, the perpendicular to the base of an associated triangle bisect the base. In the drawing we have triangle ABC that is an associated triangle because side AB equals to side AC. And according to this rule 22, the perpendicular AM to the base BC bisect the base BC. That is to say, BM equals to MC. So we can actually implement rule 22 in our drawing. Why? Because in our drawing, triangle CAQ is an associated triangle because AQ equals to AC. According to rule 22, the perpendicular AM to the base QC bisect the base QC. That is to say, it divides the base QC into two halves. The first half is QM and the second half is MC. And of course QM equals to MC. So if we define the length of QM as A, then the length of MC must be also equal to A because they are equal to each other, according to rule 22. So in the next step, we will extend the perpendicular AM by a straight line until it touches line segment PC. Okay, again, we will extend the perpendicular AM by a straight line until it touches side PC. And we define the touching point of the extended perpendicular AM if side PC. This point is point M. AM is a perpendicular, it is absolutely a straight line. Then we extended the straight line AM by a straight line, the result is AN. When we extend the straight line by a straight line, the result must be also a straight line. So AN is also a straight line. So if we focus on the right side of the straight line AN at point M, Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have the right side of AN, at point M we have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the right triangle PQC, 90 degrees plus 60 degrees, it is 150 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So, this missing angle must be equal to 30 degrees in its size. Likewise, in the small right triangle NMC, 90 degrees plus 30 degrees is 120 degrees. Therefore, this third missing angle must be equal to 60 degrees in size, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. So actually it is very easy to see that the big right triangle PQC is similar to the small right triangle NMC. So I'll explain anyway why those two right triangles are similar to each other. First of all, this angle C is a common angle that belongs to both triangles. The size of angle C is 30 degrees. Angle C belongs to the small right triangle NMC, and angle C that equals to 30 degrees in size also belongs to the big right triangle PQC. So we can write down that angle C equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So we can find out that all the angles of the big right triangle PQC are correspondingly equal to all the angles of this small right triangle NMC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. We should find out that the big right triangle PQC is similar. This is the sign of similar to the small right triangle NMC, according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. And again, from the fact that the big right triangle PQC is similar to the small right triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so NC is the missing side, so we leave it as it is. So it is actually NC over PC. PC equals to 4 units in itself according to what is given in the question. and it is equals to MC. MC equals to A according to our definition over QC. QC equals to A plus A, that is 2A. So in total, we have found out that NC over 4 equals to A over 2A. So here we have A in the numerator and A in the denominator, so A will get cancelled. So on this side of the equation we left only with 1/2. 1/2 equals to NC over 4, or NC over 4 equals to 1/2. Here we will multiply this equation by 4 and finally get that the missing side NC is equal to 4 over 2, that is 2. NC equals to 2 units in its length. This is the missing side NC, that is equals to 2 units in its length. So write it down. NC equals to 2 units in its length. In the next step, I'll copy the big triangle A and B in a new page, and we will analyze this big triangle, triangle A and B. So this is the big triangle A and B that I go from the original domain. AB equals to 5 units in itself according to what is given as a question. This is angle A and B that is equals to 60 degrees in size. Angle AB and equals to 60 degrees in size, and this is angle A and B that is equals to 60 degrees in size also. So 60 degrees plus 60 degrees is 120 degrees. And therefore this third missing angle must be equal to 60 degrees in size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So if you found out that the big triangle, triangle A and B, is an equilateral triangle. Triangle A and B is an equilateral triangle. We know that all the sides of an equilateral triangle, they are equal to each other. AB equals to 5, therefore AN must be also equal to 5, and NB must be also equal to 5 units in its length. What is the length of the missing line segment? Line segment CB. From the drawing, it is very easy to see that CB equals to NB motion C. Again, CB equals to NB motion C. So I'll write it now. The missing side CB is equal to NB motion C. So CB equals to NB equals to 5 units because it is one side of the big equilateral triangle A and B. Minus NC equals to 2 units in its length. So in total, as we found out that CB equals to 5 minus 2, that is 3. This is side CB, that equals to 3 units in its length. In the next step, we'll do another construction, that is to say, from point A, we'll go perpendicular on CB. Again, from point A, we'll go perpendicular on CB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CB. This point is point O. We define the length of line segment AO as H. AO it is actually the height to the base CB because it creates 90 degrees with the base CB. So I copy the right triangle AOB, the right triangle AOB. In the equation, we'll find out the length of side AO that equals to H. This is angle ABC that equals to 60 degrees in its size according to what is given as a question. The hypotenuse AB equals to 5 units in its length, also according to what is given as the question. Carefully, this is the right triangle AOB that is coming from the original drawing. This right triangle AOB, sinus 60 degrees equals to AO over AB. Again, sinus 60 degrees equals to AO over AB. So I write it down. Sinus 60 degrees equals to AO over AB. AO equals to H according to our definition, and AB equals to 5 units in its length according to what is given as the question. So in total we found out that sinus 60 degrees equals to H over 5. Again, sinus 60 degrees equals to H over 5. We know that sinus 60 degrees is equal to square root of 3 over 2. So square root of 3 over 2 is equal to H over 5. Here we multiply this equation by 5. And finally we get that H equals to 5 times square root of 3 over 2. So if I found out that the missing side H equals to 5 times square root of 3 over 2. Our test is to find out the area of this green triangle ABC. Now, actually it is very easy to see, to find out the area of this triangle ABC. The area of triangle ABC is equal to the base of the triangle, that is CB, times the height to the base, that is H, over 2. But again, this green triangle, triangle ABC, is equals to the base CB times the height H over 2. CB equals to 3 units in its length, and H, AO is equals to H, is equal to 5 times square root of 3 over 2. Divided by 2. 3 times 5 is 15, so in the numerator we have in total 15 times square root of 3 over 2 times 2, that is 4. So if you found out that the area that we are looking for this question, that is the area of this triangle, triangle ABC, the green triangle, triangle ABC, it is equal to either 15 times square root of 3 over 4 square units in its size. In terms of numbers, the value of this expression is equal to 6.5 square units in its size. If we found out that the area of this green triangle, triangle ABC, it is equal to either 15 times square root of 3 over 4 square units in its size, or in terms of numbers, the area of this green triangle, triangle ABC is equal to 6.5 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we'll solve the second question of this lecture. In the second question, our task is to find out the length of this line segment AP that equals to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of this semicircle. This is line segment PO that equals to 10 units in its length. This is line segment QP that equals to 21 units in its length. This is called QS that equals to 16 units in its length. This is angle PQC, that is a right angle. Again, our task is to find out the length of this line segment AEP that equals to x. We have to find out the value of x. So first of all, we will complete this semicircle to a circle. So completed the semicircle to a circle, and we will extend line segment QP by side line until it touches the circle. We will define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we will join points S and M together by straight line. By doing all those constructions, we can do peripheral angle MQS. This is peripheral angle MQS or peripheral angle SQM. Peripheral angle SQM is equal to 90 degrees in its size, and peripheral angle SQM subtend on called SM. Again, peripheral angle SQM, that is a right angle, subtend on called SM. So here we can implement rule 5. I'll repeat quickly on rule 5. According to rule 5, any peripheral angle is equal to 90 degrees must subtend on the diameter of the circle. In the domain we have a circle. This is peripheral angle MAN. This is equal to 90 degrees in size. And therefore, because of the fact that peripheral angle MAN is a right angle, it must subtend on the diameter of this circle. Peripheral angle MAN indeed subtend on the diameter of the circle because it subtend on MN, that is the diameter of this circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. We can implement rule 5 in our domain. Why? Because in our domain, this is peripheral angle MQS that is equal to 90 degrees in size, and therefore it must subtend on the diameter of the circle. Peripheral angle MQS subtend on SM, and therefore according to rule 5, SM must be the diameter of this circle. So already know, according to rule 5, and we found out that chord SM must be the diameter of this circle. So SM is the diameter of the circle. This is point O, that is the center of the circle. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of this circle. We define the radius of this circle as R, so OS equals to R. Likewise, OM is also the radius of this circle, is equals to R according to our definition. In the next step, we'll do another construction. That is to say, from point O, that is the center of this circle, we'll do perpendicular on QP. Again, from point O, we'll do perpendicular on QP. Circularly, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and QP. This point is point N. If we focus on the big right angle triangle SQM, this is angle M. We will define angle M as alpha. This is angle M. This is a common angle that belongs to both angles. Angle M belongs to the big right angle SQM, and angle M also belongs to the small right angle triangle ONM. Okay? So angle M is a common angle that belongs to both angles. We focus on the big right triangle SQM. Of the big right triangle SQM, this angle equals to alpha. This angle equals to 90 degrees. And therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle ONM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So actually it is very easy to see that the big right triangle SQM is similar to the small right triangle ONM. So we prove anyway why those two right triangles are similar to each other. Why the big right triangle SQM is similar to the small right triangle ONM. First of all, this is angle M, is equal to alpha according to our definition. Angle M is a common angle that belongs to both triangles. So we can write down that angle M equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So we found out that all the triangles of the big right triangle SQM are correspondingly equal to the triangles of the small right triangle ONM, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually found out that the big right triangle SQM is similar, this is the sign of similar, to the small right triangle ONM. According to angle similarity rule. And from the fact that the big right triangle SQM is similar to the small right triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side NO of the small right triangle ONM over side QS of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle SQM. I'll repeat again. Actually, from the fact that the big triangle SQM, the big right triangle SQM is similar to the small right triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side QS of the small right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle SQM. ON is the missing side, so limit as it is, over QS. QS equals to 16 units in itself, according to what is given in the question, and it is equal to OM. OM is the radius of this circle, is equals to R, according to our definition, over SM. SM is the diameter of this circle, that is equals to 2R. So in total, we found out that ON over 16 equals to R over 2R. We have R in the numerator and R in the denominator, so R will get cancelled. So in this side of the equation, we left only with 1/2 equals to ON over 16. ON over 16 equals to 1/2. Here we will multiply this equation by 16 and get that ON, the missing side ON, is equal to 16 over 2, that is 8. Which we found out that the length of the missing side ON is equal to 8 units. This is the missing side ON that equals to 8 units in its length. In the next step, I'll copy the small right triangle PON, this small right triangle PON in a new page we will implement the Pythagoras theorem in this form right triangle, triangle PON. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. So actually, this is the right small triangle PNO that develops from the original domain. This small right triangle PNO, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PN squared plus NO squared. And again, in this right triangle PNO, PO squared equals to PN squared plus NO squared. The hypotenuse PO equals to 10 units in its length, therefore PO squared is 10 squared, that is 100. And it equals to Pn squared. Pn is the missing side, so leave it as it is. So it is Pn squared plus NO squared. NO equals to 8, therefore NO squared is 8 squared, that is 64. So in total we found out that 100 equals to Pn squared plus 64. Here we subtract 64 from this equation. And you get that Pn squared equals to 100 minus 64, that is 36. So Pn squared equals to 36. Here we take a root out of this equation. And finally you get that the missing side Pn is equal to the square root of 36, that is 6. So if you found out that the length of this missing side Pn is equal to 6 units. What is the length of the missing side Qn? Actually we know that Qp equals to 21. The length of the missing side Qn is unknown. Again, 21 is the length of Qp. We don't know what is the length of Qn. For the moment, it is very easy to see that Qn equals to Qp minus Np. Again, Qp minus Np equals to Qn. So I write it down. I actually found out that the length of the missing side Qn is equal to Qp minus Np. So Qn equals to Qp. Qp equals to 21 in its length, according to what is given to the question. Minus Np. We just write down found out that Np equals to 6 units in its length. So we actually found out that Qn equals to 21 minus 6, that is 15. Qn equals to 15 units in its length. So the length of this missing side Qn is equal to 15 units. In the next step, we join points O and Q together by side line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle that is equals to R according to our definition. So in the next step, we copy the right triangle O and Q in your page and we will implement the Pythagoras theorem on this green right triangle O and Q. Qn equals to 15 units in its length, NO equals to 8 units in its length, and the length of the hypotenuse QO is R, it is the radius of the circle. Here by PT is the version from Pythagoras theorem. So actually, this is the right triangle Q and O that according to the original drawing. This right triangle Q and O, according to the Pythagoras theorem, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. Again, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. So I write it down. QO squared, that is the square of the hypotenuse, is equal to Qn squared plus NO squared. The hypotenuse QO equals to R, therefore QO squared equals to R squared, and it is equals to Qn squared. Qn is 15, therefore Qn squared is 15 squared, that is 225 plus NO squared. NO equals to 8, therefore NO squared is 8 squared, that is 64. So in total we found out that R squared equals to 225 plus 64. 225 plus 64 equals to 289. So R squared equals to 289. Here we take a root out of this equation and find again that R equals to the square root of 289, that is 17. R equals to 17 units in its length. So actually found out that the radius R of this circle is equal to 17 units in its length. OA is also the radius of this circle, that is equals to R. The radius of the circle equals to 17. And OA is also the radius of the circle, and therefore it is equals to 17 units in its length. But OA equals also to AP plus PO. Again, OA or AO equals to AP plus PO. O equals to AP plus PO. AP is the line segment that we are looking for in this question. It is equals to X plus PO. PO equals to 10 units in its length, according to what is given us in the question. And from this long equation, 17 equals to R equals to OA equals to AP plus PO equals to X plus 10. We derive that 17 equals to X plus 10. Again, 17 equals to X plus 10. Here we subtract 10 from this equation. We find again that X equals to 17 minus 10 is 7. So if we found out that AP that equals to X, AP that equals to X is equal to 7 units in its length. Okay, again, if we found out that the answer to the question is that the length of this slope, so line segment AP, that equals to x, is equal to 7 units. And that is the answer to the second question. So in the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our task was to find out the area of this green triangle, triangle ABC. So in the drawing, we have quadrilateral QABCP. It is given as a question that AQ equals to AC. This is angle QPC, that is equals to 60 degrees inside. This is angle ABC, that is also equals to 60 degrees inside. This is angle PQC, that is a right angle. Again, our task is to find out the area of this green triangle, triangle ABC. So first of all, we did the construction. That is to say, from this point A, we go perpendicular on QC. Again, from point A, we go perpendicular on QC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in QC. This point is point N. It's point N. Triangle QAC is an associated triangle because AQ equals to AC, and QC is the base of triangle ABC. The QC is the base of the associated triangle, triangle AQC. And according to rule 22, the perpendicular AM to the base QC, the associated triangle, triangle AQC, bisect the base QC. That is to say, QM equals to MC. If we define the length of QM as A, then the length of MC must be also equal to A because they are equal to each other according to rule 22. So in the next step, we extended the perpendicular AM by side line until it touches the side PC, until it touches side PC at this point. So we define the touching point of the extended perpendicular AM with side PC. This point is point N. So here, AM is a perpendicular, it is absolutely a straight line. Then we extended the straight line AM by straight line, and the result is AN. When you extend the straight line by straight line, the result must be a straight line. Therefore, AN is also a straight line. So if you focus on the right side of the straight line AN as point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have the right side of the straight line AN as point M, we have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the big right triangle PQC, 90 degrees plus 60 degrees is 150 degrees, and therefore this third missing angle must be equal to 30 degrees in its size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the small right triangle MNC, 30 degrees plus 90 degrees is 120 degrees, and therefore this missing angle must be equal to 60 degrees in its size according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to say that the big right triangle PQC is similar to the small right triangle, triangle NMC according to angle similarity rule. So I explain anyway when the big triangle PQC is similar to the small right triangle, triangle NMC. First of all, this is angle C that equals to 30 degrees in its size. Angle C is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if you found out that all the angles of the big right triangle PQC are corresponding equal to all the angles of the small right triangle NMC. And therefore, the big triangle PQC is similar to the small right triangle NMC according to angle similarity rule. And from the fact that the big triangle PQC is similar to the small right triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. And again, from the fact that the big triangle PQC is similar to the small right triangle MC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so we limit the CT over PC. PC equals to 4 units in itself, according to what is given as the question. PC equals to 4 units in itself, according to what is given as the question. And it is equals to MC. MC equals to A units, according to our definition, over QC. QC equals to A plus A, that is 2A. So we should find out that NC over 4 equals to A over 2A. We have A in the numerator and A in the denominator, so A will get cancelled. So in this side of the equation, we left only with 1 half equals to NC over 4, or NC over 4 equals to 1 half. Here we multiply this equation by 4, and find out that NC equals to 4 over 2, that is 2. So this is the roof of line 7 NC, that is equals to 2 units. So, in the next step, I copied the big right triangle A and B. In an equation, we analyze this big triangle A and B. This is the big triangle A and B that I copied from the original drawing. AB equals to 5 units in itself, according to what is given as the question. Those two angles are both equal to 60 degrees. So 60 degrees plus 60 degrees is 120 degrees, and therefore this third missing angle must be equal to 60 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So if you found out that triangle A and B is an equilateral triangle, because all of its angles are equal to each other. And we know that in any equilateral triangle, all the sides are equal to each other. AB equals to 5, therefore AN must be also equal to 5, and NB must be also equal to 5 units in its name. Okay, AN equals to 5 units in its name. So, what is the length of the missing side CB? From the drawing, it is very easy to see that CB equals to NB minus NC. Again, CB equals to NB minus NC. CB equals to NB minus NC. So CB equals to NB. That is one side of the equilateral triangle A and B. That is equals to 5 units. Minus NC. NC equals to 2 units in its length. So in total, CB equals to 5 minus 2, that is 3. So the length of the missing side CB is 3 units. In the next step, we did a construction. This is to say from point A, we do perpendicular on CB. Again, from point A, we do perpendicular on CB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CB. This point is point O. And we define the length of 9/7 AO as H. In the next step, I copied the green right triangle AOB in a new page and analyze this green triangle AOB. This is the green right triangle AOB that I copied from the original drawing. In this green triangle AOB, sin of 60 degrees equals to AO over AB. Again, sin of 60 degrees equals to AO over AB. AO equals to edge and AB equals to 5. So sin of 60 degrees equals to edge over 5. Sin of 60 degrees is square root of 3 over 2. So square root of 3 over 2 equals to edge over 5. Here we multiply this equation by 5 and find out that edge equals to 5 times square root of 3 over 2. So this inside AO that is equals to edge is equals to 5 times square root of 3 over 2 units in its length. Our test is to find out the area of this green triangle ABC. So what is the area of the green triangle ABC? From the drawing, it is very easy to see that the area of this green triangle ABC must be equal to the base CB times the height edge over 2. Again, the green triangle ABC must be equal to the base CB times the height edge over 2. CB equals to 3 times the height edge. Edge equals to 5 times root of 3 over 2. So it is 3 times the height edge, that is 5 times root of 3 over 2, divided by 2. So in total, the green triangle ABC equals to, in the numerator we have 3 times 5, that is 15. So in total, the numerator of this expression we have 15 times root of 3, divided by 2 times 2, that is 4. So if you follow the area of this green triangle ABC, it is equals to 15 times root of 3 over 4 square units in its size. On terms of numbers, the value of this expression, 15 times root of 3 over 4, is 6.5. So if you follow the area of this green triangle ABC, it is equals to either 15 times root of 3 over 4 square units in its size. So in terms of numbers, the area of this green triangle ABC is equal to 6.5 square units in its size. So we finish with the first question. In the next step, I presented to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the length of this short line segment AP is equals to x. We have to find out the value of x. So in the drawing you have a semicircle. We know that point O is the center of this semicircle. This is line segment PO, that is equals to 10 units in its length. This is line segment QP, that is equals to 21 units in its length. This is called QS, that is equal to 16 units in its length. This is angle PQS, that is equals to 90 degrees in its size. Again, our task is to find out the length of this short line segment AP, that is equals to x. We have to find out the value of x. So first of all, we completed this semicircle to a circle, and we extended line segment QP by side line until it touches the circle. We define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we join points S and M together by side line. By doing all those constructions, we get the peripheral angle SQM. This is peripheral angle SQM. This is peripheral angle SQM. This equals to 90 degrees in its side. And peripheral angle SQM subtend on chord SM. Again, peripheral angle SQM, that is a right angle, subtend on chord SM. And according to rule 5, any peripheral angle that subtend on any peripheral angle that equals to 90 degrees in its size must subtend on the diameter of the circle. Again, according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. Peripheral angle SQM is equal to 90 degrees in its size, and therefore it must subtend on the diameter of the circle. Peripheral angle SQM subtend on SM, and therefore according to rule 5, SM must be the diameter of the circle. So SM is the diameter of the circle, therefore OM must be the radius, OM must be the radius, and OS must be also the radius of this circle. We define the radius of this circle as R, so OM equals to R, and OM equals to R, and OS also equals to R. The number of the radii of the circle is equal to R according to our definition. In the next step, we did the construction, that is to say from the center of this circle, that is to say from point O, we do perpendicular on QP. Again, from point O, we do perpendicular on QP. So okay, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the construction. We define the touching point of the perpendicular from point O and QP. This point is point N. So we have here in the big right line SQM, we define this angle as alpha. So angle alpha is a common angle that belongs also to the small right line ONM. So angle alpha is a common angle that belongs to both triangles. belongs to the big right triangle SQM, and angle alpha belongs to the small right triangle ONM. So if you relate to the big right triangle SQM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the small right triangle ONM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. It is very easy to see that the big right triangle SQM is similar to the small right triangle ONM. So, why those two right triangles are similar to each other? First of all, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that all the figures of the big right triangle SQM are correspondingly equal to all the figures of the small right triangle ONM, and therefore the big triangle SQM is similar to the small right triangle ONM according to angle similarity rule. And again, if you found out that the big right triangle SQM is similar, this is the sign of similar, to the small right triangle ONM according to angle similarity rule. And from the fact that the big right triangle SQM is similar to the small right triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side SQ of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle SQM. And again, we will derive that side ON of the small right triangle ONM over side SQ of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle SQM. ON is the missing side, so we leave it as it is, over SQ. SQ equals to 6 units in its left according to what is given in the question, and it is equals to OM. OM is the radius of this circle that is equal to 1 over SM. SM is the diameter of this circle that is equals to 2R. So in total, you actually found out that ON over 16 equals to R over 2R. We have R in the numerator and R in the denominator, so R will get cancelled. So in this side of the equation we left only with 1/2 equals to ON over 16, or ON over 16 equals to 1/2. Here we multiply this equation by 16, and finally found out that ON equals to 16 over 2, that is 8. ON equals to 8 units in its length. This is the missing side ON, that equals to 8 units in its length. In the next step, I commit the small right triangle NOP in a new page and implemented the Pythagoras theorem on this small right triangle NOP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the square of the perpendiculars. This is the small right triangle PNO that I commit from the original drawing. In this small right triangle PNO, OP squared, that is the square of the hypotenuse, equals to ON squared plus NP squared. OP is 10, therefore OP squared is 10 squared, that is 100, and it is equals to PN squared. PN is the missing side, so we leave it as it is, plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total, we found out that 100 equals to PN squared plus 64. Here we subtracted 64 from this equation, and finally found out that 100 minus 64 is 36, so Pn squared equals to 36. Here we took a root out of this equation, and finally found out that Pn equals to the square root of 36, that is 6. So if you found out that this is the missing side NP, or Pn, that equals to 6 units in its length. What is the length of the missing 97QN? From the drawing, it is very easy to see that Qn equals to Qp minus Np. Again, Qp minus Np equals to Qn. Qn equals to Qp minus Np. So Qn equals to Qp, that is 21. According to what is given in the question, minus NP. We just found out that NP equals to 6. So in total, Qn equals to 21 minus 6, that is 15. This is the design Qn, that is equals to 15 units in its length. In the next step, I copy the grain right triangle Q. In the next step, we join points Q and O together by straight line. Q, O, or OQ is the radius of this circle, that is equal to R. So, in the next step, I copied the right grain triangle Q and O in a new page and implemented the Pythagoras theorem on this right grain triangle Q and O. So actually, this is the right grain triangle Q and O that are going from the original domain. In this right triangle Q and O, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. QO is R, therefore QO squared is R squared, and it is equals to QN squared. QN is 15, therefore QN squared is 15 squared, that is 225, plus ON squared. ON is 8, therefore ON squared is 8 squared, that is 64. So in total, we found out that R squared equals to 225 plus 64. 225 plus 64 is 289. So R squared equals to 289. Here we took out all of this equation and found out that R equals to the square root of 289, that is 17. So we found out that the radius of this circle R equals to 17 units. So we know that OA is also the radius of this circle, that is equals to 17. The radius of this circle R equals to 17. OA is also the radius of the circle, that is equals to R. But OA, the radius OA also equals to OP plus the radius OA equals to AP plus PO. Again, the radius OP, the radius OA equals to AP plus PO. The radius OA equals to AP plus PO. AP equals to X, that is the line segment that we are looking for in this question, and PO equals to 10. And again, AP equals to X and PO equals to 10. And from this equation, we derive that 17 equals to X plus 10. Okay, 17 equals to X plus 10. Here we subtract the 10 from this equation and finally found out that X equals to 17 minus 10, that is 7. So AP is equals to X is equal to 7 units. The answer to the question is the length of this short line segment AP, that is equal to X, is equal to 7 units. Again, the length of the value of X is equal to 7, or AP is equal to X is equal to 7 units. Okay, thank you very much.